Hello, and welcome to the last lab topic regarding computer networks for the year 2020. In today's lab, we're going to discuss the Internet Control Message Protocol, and we're going to go over two of the simplest and yet most effective tools of gathering information when regarding the connection availability of one host or another. As such, I'm going to remind you to please put on your attendance on the virtual campus, and also please write down your names in the chat windows so that I can correlate the two messages. I'm going to share my screen now. Please be aware that this meeting, as always, is recorded, and the movie will probably show up on the virtual campus later this week. As stated before, today we're talking about Icmp&Dns, where I know that DNS is one of the projects some of your colleagues have already discussed, but I just wanted to point out a few more details that I believe were a bit skimmed over in their presentation. So we're going to go over the Icmp protocol, the ping command, the traceroute functionality, and the DNS functionality and general description as, very short topics that we can go for. I forgot to ask, can you see my screen? You usually could,
yes,
but
yes.
Okay, thank you. So, Internet Control Message Protocol, or Icmp, is the protocol that we use nowadays to verify if a host is reachable or not, and how it can be reached. As you can see, the protocol is under the gaze of the internet layer. Which one is the internet layer?
The IP, right?
Yeah. But when referring to the TCP/IP stack, protocol stack, do you remember the TCP/IP protocol stack?
It's the one with 4 layers, right?
Yeah.
It's right. It's the one below application level.
Try
right?
again.
It's not internet. Wait.
What's the first one?
It's the physical layer.
It just has a little bit of a different name called network access.
Network access, okay.
Okay. And then we have
the transportation
layer.
Nope. Then we have the internet layer, and afterwards we have transport and applications.
I thought it's the other way around.
Nope. Sorry about that. Sorry to burst your bubble. But the internet layer is the second one in the TCP/IP stack. As you can see, it's quite simple. It doesn't have much of information within it. It has 3 fields, namely type, code, and checksum. We've met checksum before, namely this one, and just as before, it's usually the last one in the field. We've had checksums at the MAC, at the Ethernet frame. We had the frame check sequence that had a checksum included. We had checksums at the transport layer when referring to TCP. And did we have it at UDP? Do you remember?
UDP doesn't have a checksum, right? That's why it's used. It doesn't actually check for errors. It doesn't care.
Mm-hmm. Okay. So, worth mentioning that the type message is the one that we're going to use. It has 3 basic, not tasks, but 3 basic ways of working. You can have echo messages of request or reply. You can have inter-router messages, and you can have a request timeout field. Now, this request timeout is based on the TTL value. TTL stands for time to live. I forgot to put this on the slide, but you will find it in the lectures when addressing the Internet protocol, the IP protocol. Now, the TTL field, we're going to go over it in a little bit. It's just like, but you, as a general fact, just know that TTL, namely time to live, is basically a counter. And whenever you pass through a router, that counter gets decremented. So that's, I don't know, value -1, and that's that. Now, when addressing the Icmp and mainly the ping command, have you ever used the ping command?
Yes.
Let's try it now. Not CD burner, but command prompt. And I'm going to go with ping www.google.com. And we see here the followings. We see that the command has been executed when we pinged Google. We see the IP address that is attached, that is currently attached to Google. And we have 32 bytes of data. Those 32 bytes of data are sent in 1, 2, 3, 4 packets from our host, namely from our computer to the destination, namely to Google. We see that each packet has the 32 bytes, and we see the times that it reached the site and the TTL value, the time to live value for each packet. Now, worth mentioning is this particular field, namely the time one. The time is from the time we said an Icmp echo request. As it moves throughout the system, it reaches the destination, and the destination will send an echo reply. The time that we see here, for instance, which is smaller than 1 millisecond, is the time from the time we sent. It's the time computed from the moment we sent the echo request to the moment we received the reply. And here in this particular graph, we see the types of messages, almost all of them. Namely, we see that we have Icmp requests, replies, and right here you see that you have intermediate systems. Now, these intermediate systems are routers. From when you send the packet from one router to another, the Icmp message structure changes a bit and states that it's been used to pass on information between two routers. I'm not going to go over this particular graph for too long, and basically that's all that I wanted to show you, namely to see that the time computed here or in the slides or whenever you hit the ping command is the time from the request to the reply. Now, the main purpose of the ping command is to determine whether a host is reachable or not, and that's it. You can see here that we have examples in which we will send pings to IP addresses. We will send them to host names, to the hosts such as Google or Facebook or Yahoo or whatever. And the behavior of the tool is the same. More so, in some cases, you might get messages such as request timeout. Now, these particular messages are sent when you don't actually reach the destination. More so, not necessarily when you don't reach it, but when you don't reach it because this TTL value has gone down to 0. If a particular host does not answer or has a filter blocking Icmp commands, blocking the pings, for instance, the message will be changed from request timeout to something else. Does anyone know it? Have you ever seen other types of messages in ping? There is one more type of message, namely a host can't answer or host does not respond. That's how you know the host is there, however, it's blocked behind some sort of a firewall. Now, usually we use the ping command like this, and that's that. However, we can also see these lines in Wireshark, and you can see that each of them in the info tab, you have requests and replies. Those two will be paired by identifiers if you open up the the packet, the frame. And that's about it for Wireshark and ping. Again, is anyone that hasn't used it ever?
I didn't.
Never up until now?
No.
Whoa. Okay. So the first thing that you need to remember is don't necessarily open Wireshark because you don't need it. All the information you actually need is whether it's a command prompt or a Linux terminal. You can just type in ping and the IP address or the destination that you want. And you'll get a reply such as this. What's worth mentioning is that Windows sends only 4 packets, Linux and iOS send as many packets as they want until you actually stop them. Sorry. Now, the last command that we're going to talk about in this lab, the entire lab, which is weird, a lot weirder actually saying it, but anyway, is the traceroute command. Now, if ping gives us an answer whether the host, the destination, is reachable or not, the traceroute command will give us the entire flow, the entire path that the packet went to get there. So first, it goes to this router, and then this one, and this one, and this one, and so on until it reaches the destination. Traceroute goes by traceRT in Windows and traceroute in Linux, and I'm not sure in iOS. As before, you can use it while by typing in the IP or the host name. What's nice, and you might notice it, that we've pinged or tracerouted to the same google.com. One second, Paul, and you'll see here that the IPs are different. Go on, Paul. Do you have a question? You raise your hand. Ah, okay then. So you don't have to worry about it. Again, at any time, if you have questions, please do tell, and we can look over them. Now, as you see here, that we have the times that the packet was sent, sorry, from one system to another, and from the beginning all the way to the end. Now, this is my first hop. This is my wireless router's address. This is the first operator's address, the first router of the operator that is in my path. And I have no idea what the others are. Worth mentioning that on some of them you will see straight IP addresses, others you will see host names as well. and you get messages such as trace complete when you reach the destination. And that's basically it for traceroute as well. The only other thing that we have to mention, and now we're going back to the TTL part, is how traceroute actually functions. Now, it's not quite that difficult to understand. It's quite easy, so please pay attention for 1 or 2 seconds or minutes and you'll figure it out. So we want to get from this PC to this one while using different values of TTL. The first thing that we're going to do is send the packet with a TTL value of 1. When the router receives a packet, so when the router receives a packet, routers are lazy. They're pretty much like me in that way. So the first thing that they're going to do when receiving a packet is take the packet, unscramble it all the way to the TTL part, and subtract 1. If the new value after the subtraction reaches 0, the router won't do anything to the packet. It will just discard it. In our case, we sent a TTL packet of 1. It will reach, not a TTL packet, a packet with a TTL of 1. It will reach the first router. The router will do a TTL minus 1. It will reach 0, and it will not do anything with it. It will just drop it. Sorry. While dropping it, it will send back an error message saying that there's no reaching in sight. If we send the packet with a TTL number of 2, it will go to the first router. The first router will do a TTL minus 1, reaching the value of 1. And it will go like, oh, foo, there's still a TTL, so that means I still have to process this packet. It will look for the destination PC in its area of coverage. It will see that it doesn't do, that it's not there, and it will send the packet forward. Reaching the second router, we have a TTL value of 1, and similar to the previous case, the first thing we do is do a TTL minus 1 and discard the packet since there's no reply. And so we go on and we see that in order to reach the destination, we actually have to use a TTL value of a minimum number of hops or routers plus 1 to reach the destination. Now, all of these error messages here that you see going back and forth are the messages you see here in the trace route. So whenever you reach the first router, you come back and send, I've reached the first router in 4 milliseconds. I've reached the second router in 17 milliseconds. I've reached the third router in 10, and so on. Please note that these are not necessarily ordered because you can go on, sorry, because you can go on parallel paths to the destination. A short question. Do you understand how this principle works?
So how does our computer know what the initial TTL to give?
It doesn't. It grants you a random number. You see here that tracing route to Google over a maximum of 30 hops. That means a value of TTL of 30. In the ping, we go to a TTL value of 128 in this particular picture, 53 here, and 53 in my case currently as well. So the value is chosen randomly.
So if you choose a value too small, it will tell you that the host is not reachable, but in fact, the TTL value was too low?
Yeah.
So that's why you have to ping several times in order to be sure.
Yeah, exactly. Let's see if I have. Now this is if I'm not mistaken, last time, even though you didn't work with me because I had a small issue to take care of, you worked with my colleague and he showed you a little bit of packet tracer, didn't he?
Yes, he did.
Did you like it?
It was interesting.
Okay. Not the answer I would have given, but yeah, sure, thank you. Okay, Packet Tracer is a free tool and you can just log in as a guest. You just have to wait for a couple of seconds to confirm that you're a guest and you can use it. And you see here that we have already the connection made that should have been done last time. Over here at the PC, we have an IP address of 192.168.10.67. And I'm going to go in this particular area on this PC on the command prompt. It's similar to the Windows one. And I'm going to go to ping 192.168. I can't remember what the values were. And we can go here. We can even ping the gateway because it doesn't matter. 10.65. 10.65. You see, we got a request timeout. And we should get another one. And then we get finality. So we get to the end router. After the pathway, so to speak, was already established, you see that on subsequent trials, we get all the packets with no loss whatsoever. Okay, so this is similar to doing the ping and the trace route over here. The TTL values need to actually match. I have never seen a TTL value bigger than 254, and this value I have only seen it in simulations. So usual values go up to, I don't know, 128 and less than 64 to be on most cases.
So that one needed 254 hops to reach its destination?
No, that's the random number. So if you have to go to 255 hops, I won't send packets of that size. So it's a maximum number of hops that the packet will be allowed to stay in any network whatsoever. You can't stay for longer than that. And that is why usual values go to, I don't know, a maximum of 64 or something like that. Do you understand?
Yes, but does it tell us somewhere what was the number of hops needed?
No. In order to find the number of hops, you actually have to use the traceroute command and you get a graph similar to this one. And it will tell you that from my PC to Google, I went to over 9 routers over a maximum of 30. So if we would have needed 31 hops, I wouldn't have reached Google, but I only need 9.
Okay, I got it.
Okay. The last thing I wanted to talk about is a little bit of about DNS. As you've seen in these particular examples, we typed in Google and it gave us an IP address, and then it gave us another IP address because there are some systems that do use more than one IP addresses, especially the large hosts and clients such as Google, Facebook, and so on. They don't rely on a single server, so there is not only one server for Google or Facebook, and you will be redirected randomly, not necessarily randomly, but you will be redirected to the one that can process your request. However, so that you don't have to remember that on Google meant 216.58 something something, and at some time else it might go to 172.217 and so on, we use the simple name as google.com. The domain name system or server takes care of that particular problem, and it's important to know that it's a database, it's a hierarchical database. And you see here the message structure that leaves your PC and goes to a DNS server. First going like, well, I need to get to Google. Well, for Google, please use this IP address. And then you actually go to Google and make an HTTP request to the IP. Throughout the internet, you will never use actual names. The internet is connected via IP addresses, and this particular system, the DNS, makes sure that you don't actually have to remember the IP addresses. And when I stated that it's a hierarchical database, it states the following. Whenever I go to Google or Facebook or whatever site you want, the first thing that the computer will do is ask the DNS, the database on the local computer or the tablet or the phone or whatever. And it goes like, well, I need directions to Google. Well, Google, which is the first database on your particular computer, goes like, well, I don't know what the IP address of Google is. And then your database from your computer will ask another DNS server. And so on. It's a hierarchical structure. You go up the hierarchy until someone actually knows the address that you want. As you can see here, I'll try another DNS server. It goes on to the third, and the third goes like, oh, I know what the IP address for Google is. It's this one. And the message goes all the way back, and then you can actually connect to the end system. This is the clearest picture that I found that explains this. Do you understand it? Do you understand how the system works?
Yes.
That's one yes.
Yes.
Go for two. Oh, okay. Okay. This is actually the only thing that I did not see in the presentation regarding DNS on well, in the presentation that your colleagues made, and that's why I wanted to show it to you. Again, each device has its own DNS cache, its own DNS database. However, it doesn't actually contain all entries whatsoever to everything in the world, because then the database will be huge. And that is why we have a distributed database, and you have to go over several steps to get the information that you want. It says here that we're going to open a trace and see what happens. You have the ability to do it by yourselves at this point. If you want, all you have to do is look at the slides and open Wireshark and type in ICMP here as a display filter and work on the two commands that you have seen. And that's actually it for the Computer Networks lab. You will not receive any homework for this one as well. It's just, good to know. You will, on the other hand, receive questions probably at the exam from it. Namely, what does a ping look like? What does a ping do? What does a trace route do? What does a trace route look like? For instance, we can give you an image such as this and ask which command will give this output or stuff like that. And that's that.
Would we have to type any response or just select one?
Select. Selecting is easier.
That's what I wanted to hear.
So, if there are no more questions, that's it for me for today. and I can't wait for next week until when we're going to have a feedback session. Thank you for your attendance and see you next time. Stay safe.
Bye.
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 Bye-bye.
Bye.
Bye.
By the way,
Yeah.
I need to ask you some questions privately. Can I send you an email?
Yeah, definitely. You can send an email or use the virtual campus for it.
I